Welcome back to Practical PyTorch. In this video you'll learn what a loss function is, the one number that says how wrong your model is right now. You'll meet the two you'll use most, mean squared error for numbers and cross-entropy for classes, and one quiet bug that catches almost everyone. Before a model can improve, it has to know how wrong it is right now, and not as a paragraph, as a single number. This line computes it. Loss equals loss function of the prediction and the target. That number is the loss. It says how wrong the model is on this data, and choosing which loss to use is really choosing what the model will learn. This video has 4 parts. First, the big idea. The loss is one number how wrong the model is as a single value. Second, regression, when the model predicts a number. There we use mean squared error, the mean of the squared errors. Third, classification, when the model picks a class. There we use cross-entropy, and it's scored on the raw scores, the Logits. And fourth, the rule that saves you a silent bug. Pass Logits, not probabilities. Get it wrong and the bug is silent. Let's start with the big idea. Whatever the model is doing, the loss turns it into one number, and that one number is what training tries to shrink. Picture a tiny model with a single weight, called W. A real network has millions of weights, but one weight is the picture that fits on a slide. Let's set up the 2 axes. The horizontal axis is that weight. W slide it left or right, and you're dialing the one knob this model has. The vertical axis is the loss, how wrong the model is. So every value of W gives you one height, one loss. Now sweep W across the axis and mark the loss at each value. The points trace out a bowl, high on the sides, low in the middle. The bottom of the bowl is special. That's the one W with the smallest loss, the best this model can do. We call it the minimum. There's exactly one lowest point, and reaching it is the whole goal of training. When training begins, W is just some starting value you didn't pick carefully. So the dot lands here, high on the side of the bowl. High on the curve means a high loss. The model is quite wrong at this W, and that's completely normal at the start. The whole job of training is to walk this dot down the curve, toward the minimum. That same walk is the next video. Today we just build the number it's walking on. So which loss do you actually use? It depends on the task. Let's start with the case where the model predicts a number. When the model predicts a number, a price, a temperature, that task is called regression. For regression you score it with mean squared error, or MSE. It's the mean of the squared errors, how far each prediction is from its target. The second row is still empty. That's classification coming up. Let's score a real example. First, we import torch.in.functional and call it f. That's where the loss functions live. These 4 predicted prices go in, paired with the 4 true prices they're aimed at. Each prediction is a little off from its target. Now we call f.mse loss on the predictions and the targets. Notice reduction equals mean. That's what turns 4 separate errors into one number. And out comes tensor, 0.2875. 4 predictions, 4 targets, one number. That number is the loss. So no matter how many predictions go in, mean squared error hands you a single score for the whole batch. Let's see where that number comes from so it isn't magic. The 4 errors are minus 0.5, 0.5, 0.1, and 0.8. Square each one and add them up. That gives 1.15. Then divide by 4 the number of predictions. And remember, mean just means average. 1.15 over 4 is 0.2875, exactly the number we printed. Why square? Squaring drops the sign, so an error above the target and one below both count as wrong, and it makes a big miss hurt much more than a small one. That's regression, where the model predicts a number. Now the other big case, when the model picks a class and the loss changes. When the model picks a class instead, cat, dog, or bird, that task is called classification. For classification, you use cross-entropy, not mean squared error. And now the table is complete. A number gets MSE, a class gets cross-entropy. The task on the left picks the loss on the right. A classifier gives one raw score per class. This model outputs tensor 2, 0.5, 0.1, 3 scores for 3 classes. Those raw scores have a name, Logits. Class 0 with the 2 is the true answer. A logit is a raw score, not a probability. A higher logit just means a more favored class, so class 0 is winning. The step that turns logits into real probabilities that add up to 1 is called softmax. Let's score those logits. Same 3 raw scores, tensor 2, 0.5, 0.1. The label is tensor 0. That says the correct class is class 0, the first one. Now we call f.cross-entropy, and we pass the logit straight in along with that label. The raw scores, not probabilities. The loss comes back as tensor, 0.3168. Keep that number in mind. It's the correct answer, and we'll compare against it soon. Here's the key idea. F.cross-entropy runs the softmax itself, inside, and then scores how much probability landed on the true class. You give it logits, it does the rest. That one fact that cross-entropy owns the softmax leads straight to the most common mistake beginners make. Let's try it on purpose. To see what cross-entropy does inside, let's run the softmax ourselves. We call f.softmax on the same logits, with dim equals 1 and store it in probs. Then we just look at probs, the probability softmax made from those raw scores. They come out as 0.7285, 0.1625, and 0.1090. 3 real probabilities, and they add up to 1. Class 0 already holds about 0.73 of the probability, and this exact step is the one f.cross-entropy does for you, inside itself. Now the mistake. We take those probabilities and feed them to f.cross-entropy, thinking we're being helpful. Probs this time, not logits. And look, it runs. Out comes tensor 0.7448. No error, no warning, just a number. But that number is wrong. Cross-entropy expected logits, so it ran softmax on your probabilities a second time, normalizing what was already normalized. The correct loss was 0.3168. This says 0.7448. Nothing crashes, and the model quietly learns worse. Put them side by side. Pass the logits and cross-entropy gives 0.3168. That's the right answer. Pass the probabilities instead, and the same call gives 0.7448. Same prediction, same true class, 2 different losses. So the rule to memorize is simple. Pass logits to cross-entropy. It owns the softmax. Give it probabilities and the loss is silently wrong, nothing raises, and the model just learns worse. Let's bring it together. The loss is one number, how wrong the model is right now, and the number that backward starts from. When the model predicts a number, that's regression, and you use mean squared error, the mean of the squared errors. When the model picks a class, that's classification, and you use cross-entropy, scored on the Logits, the raw scores. And reduction equals mean, is what folds many errors into the single number you actually minimize. Quick check before we go. You softmax the Logits yourself, then pass those probabilities to f.cross-entropy. What error do you get? Pause the video and predict. Here's the answer, and it's a trick. You get no error at all. It just runs. Cross-entropy softmaxes your probabilities again, so the loss is silently wrong, 0.7448 instead of 0.3168, and the model trains on the wrong signal. The silence is exactly why this bug survives. So now you have the one number. You can measure how wrong the model is with the right loss for the task. But a number alone doesn't fix anything. The loss is the one number training wants to make small. The next video's optimizer takes the step that lowers it, walking that dot down the curve. See you there.